Okay, so we have a signal processing practice final exam. Let's begin. Number one, consider this system governed by the following. This differential equation, where the input is x of t equals u of t e to the negative 2t with zero initial conditions. Part A, determine the transfer function h of s. Part B, determine the poles and zeros. Part C, determine if the system is bibo stable. Part D, find the impulse response h of t. Part E, determine the output y of t. So this is a continuous time LTI system analysis, linear time invariant analysis problem. So for part A, we write this as y double prime plus 4y prime plus 5y equals 2x of t. Taking the Laplace transforms with zero initial conditions, we have s squared plus 4s plus 5, that quantity. Y of s equals 2 xs. H of s equals y of s over x of s, and equals 2 over s squared plus 4s plus 5, and s squared plus 4s plus 5, completing the square. If we write it in that form, if we rewrite it as s plus 2 squared plus 1, that's the equivalent form, and now we could write h of s equals 2 over s plus 2 squared plus 1. For part B, determining the poles and zeros, there are no finite zeros because the numerator is constant. And for the poles, s squared plus 4s plus 5 equals 0. So negative 4, s equals negative 4 plus or minus the square root of 16 minus 20 over 2. S is going to equal negative 2 plus or minus j. For part C, a continuous time causal LTI system is bibostable if all poles have negative real part. Both poles have real part negative 2, so it is bibostable for the bounded input, bounded output. For part D, find the impulse response h of t. So capital H of s equals 2 over quantity s plus 2 squared plus 1. We're going to use the inverse Laplace of 1 over s plus a squared plus b squared, and that's going to equal negative 1 over b e to the negative at sine of bt u of t. And here a equals 2, b equals 1. So h of t equals 2e to the negative 2t sine t u of t. Okay, and now moving along to letter E, determine the output y of t. So sorry about that. So determining the output here of y of t, x of s equals 1 over s plus 2, y of s equals h of s, x of s. That equals 2 over quantity s plus 2 times this s plus 2 squared plus 1 inside the parentheses there. We're going to let u equal s plus 2. Then y of s equals 2 over u times quantity u squared plus 1. Decomposing this, 2 over u times quantity u squared plus 1 equals a over u plus bu plus c over u squared plus 1. 2 is equal to a times quantity u squared plus 1 plus bu plus c u. 2 equals a plus b u squared plus cu plus a. A equals 2, c equals 0, a plus b equals 0, b equals negative 2. So y of s equals 2 over s plus 2 minus 2 times the quantity s plus 2 over s plus 2 squared plus 1. Invert, y of t equals 2e to the negative 2t minus 2e to the negative 2t cosine t, and y of t equals 2e to the negative 2t times the quantity 1 minus cosine t u of t. So that is for number 1. Moving along to number 2. Okay, so we're given a periodic signal as period t equals 4, and this piecewise function here for x of t repeated periodically. Let me just, okay, so this is x of t equals, for 2, interval 0 is less than t is less than 2, and for -1, 2 is less than t is less than 4. So for part A, we find the complex Fourier series coefficients. So let's see what we could do here. So for the Fourier series and harmonic content problem, for part A, we could say omega naught equals 2 pi over t equals pi over 2. And we have what was given here. So our complex Fourier coefficient C sub k equals 1 over t, integral 0 to t x of t e to the negative jk omega naught t dt. C sub k equals 1/4 bracket integral of 0 to 2e to the negative jk pi t over 2 dt plus integral from 2 to 4 -1 e to the negative jk pi t over 2 dt, close bracket. For k equals 0, c naught equals 1/4 times 2 times 2 plus 1 times -1 times 2. So c naught equals 4 minus 2 over 4 equals 1/2. So c naught is 1/2. And now, for k is not equal to 0, we're going to let alpha equal k pi over 2. C sub k equals 1/4 times bracket 2 times quantity 1 minus e to the negative j2 alpha over j alpha minus e to the negative j2 alpha minus e to the negative j4 alpha over j alpha. E to the negative j2 alpha equals e to the negative jk pi. That equals -1 to the k. And and e to the negative j for alpha, that equals e to the negative j2k pi. That equals 1. So our c sub k is going to equal 1 over 4j alpha bracket 2 times quantity 1 minus -1 to the k minus this quantity -1 to the k minus 1, close parentheses, close bracket. So c sub k equals 1 over 4j alpha bracket 3 times quantity 1 minus -1 to the k, close bracket. And alpha equals k pi over 2. So we're going to wind up getting c sub k equals this piecewise function 1/2, where k equals 0, and 3 times quantity 1 minus -1 to the k over 2jk pi, where k does not equal 0. And for even k, c sub k equals 0, and for odd k, c sub k equals 3 over jk pi equals -j times 3 over k pi. So that's for letter A. For letter B, they want us to find the trigonometric Fourier series form. So for letter B here, trigonometric form, since c sub k is purely imaginary, for odd k, only sine terms appear. X of t equals 1/2 plus the summation here of k equals 1 to infinity of b sub k sine of k omega naught t. Relationship here, c sub k equals a sub k minus j bk over b sub k over 2. B sub k is -2 im ck. For odd k, c sub k is -j times 3 over k pi. So b sub k is 6 over k pi. For even k, b sub k equals 0. And x of t equals 1/2 plus summation here, k equals 1 to infinity, where k is odd. 6 over k pi sine of k pi t over 2. For part C, they want us to determine the DC component. So the DC component, x sub DC, that's just going to equal 1/2. For the total power, part D, they want us to find the total signal power using Parseval's theorem. So the total power here, P equals 1 over T, integrated from 0 to T, magnitude of x of T squared dt. So that equals P equals 1/4 bracket integral 0 to 2 4 dt plus integral here 2 to 4 1 dt. Performing the computation, our P equals 5/2. And for part E, estimate the percentage of power in the first three harmonics. So the power here in the first three harmonics here, power from DC, P sub DC equals C naught squared equals 1/4. For harmonic K, the contribution is 2 times that magnitude, C sub K squared. Now, only odd harmonics are going to contribute, so the first three non-zero harmonics, K equals 1, 3, and 5. 2, magnitude of C sub K squared, that equals 2 times 3 over K pi squared equals 18 over K squared pi squared. So P sub 135, that equals 18 over pi squared times the quantity 1 plus 1/9 plus 1/25. And that's going to give us 1.1511 approximately. So P sub 135, that's 18 times 1.1511 over 9.8696, which is about 2.10. And the percentage of the total, we take the 2.10 dividing it by 2.50, we get about 84%. So about 84% of the total power is in the first three harmonics. Okay, so that's part one. Thank you very much and have a great day.